Okay, today we're going to start talking about Gauss's law, but before we go and talk about Gauss's law, we'll talk about a quantity that we'll use a lot, that's flux. And when we talk about electric field, we'll talk about electric flux. Later on, when we go to magnetic field, we'll talk about magnetic flux. What is the flux? It's the number of field lines coming out from the surface. That's it. It's the number of field lines coming out from the surface. This is the meaning of flux. It has to be a closed surface though, yes.
I thought field lines were imaginary.
They are imaginary, but still, this is the meaning of number of, you measure the strength, number of field lines means the strength of the electric field. So it's a measure of the strength of the electric field within closed surface. So this is the meaning of flux. So let's assume, guys, those are field lines. And this is my surface. How many feet, what is the flux on that surface? 1. It's 1. Now what is the flux on the surface? 4. That's it. This is the definition of flux. Okay? It has to be coming out from the surface. So now on that surface, what is the flux? 1. Okay? Now assume that this room is our surface, and assume that there is an arrow that goes inside from that wall and goes out from that wall. It goes into that wall and out from that wall. What is the flux on the whole surface?
0.
Why is it 0? Because the number of field lines that goes in equal to the number of field lines that goes out, so the net number of field lines here is 0. I'm talking about arrows. Yes. Electric charge where? On the surface. Where are those electric charges come from? No. The presence of field lines does not mean that there is an electric charge inside the room. So if we have field lines does not mean that there is electrons. It's field.
They carry electrons.
No. The field does not carry electrons. Field means that there is a field. But if there is electrons in the field, they will move with the field. But in vacuum, where there is no charges at all, there is no matter at all, if there is a field, nothing is going to move. No charge will move. You're taking us a little bit further. But anyway, guys, so again, flux, it's just number of field lines, nothing more than that. So as I said, and when asked, if we have field arrows that goes from that wall, and they leave the room from the other wall, what is the flux in the whole surface, that whole closed surface? It's going to be 0 because the number of field lines in, the number of lines in equal to the number of lines out. And this is the meaning of field lines. Oh, sorry, flux.
In and out, or
In and out. In and out. Now we have 4 lines coming into that surface, and 4 lines leaving that surface. So we're talking about the number of field lines out of the surface. So if you talk about the whole surface of the room, then the flux is 0. But if you talk about that wall only, we will have a flux. If you talk about that wall only, we will have a flux. Okay? Yes? Okay. Taking this a little bit into what we study, electricity. I'll go to the board. Sure. We have a sphere we have a sphere, and we have a charge Q outside of that sphere. What is the flux on the surface of that sphere? Zero. So Sharif is saying there is no flux, and he gave us an explanation. What was the explanation again?
explanation ان positive charge electric field بيبقى طالع منها كده ويساعد ان الفلكس بيبقى طالع من السيرفيس.
Right? This is the electric field from that positive charge, right? Now, what is the flux on that sphere? Why is it zero? Because the number of field lines coming into the sphere equal to the number of field lines going out, so the total flux on that sphere is going to be zero. Okay? I'm going to take the same sphere again, and I will move the charge in here. What is the flux? Do we have flux? Yes. Because if we draw the field lines again, all of them are leaving the surface. All of them are leaving the surface. So that actually we will have a flux in here. So in order to have a flux, the charge has to be inside the surface. If the charge outside the surface, the flux on that surface is going to be zero. It's not zero. That's a good thing. Now that's our next step. Here we have a zero flux. We have a non-zero flux. And I forgot your name, I'm sorry. Omar is saying, then he said, can we quantify that flux? Can we calculate the flux? That's easy. Flux equal to the integration of E dot the area. The integration flux, sorry, I'll have to write it here for a minute. Flux, and I'll say flux E, because we're going to have later on flux phi B, which is the magnetic flux. Now we're talking about the electrical flux, which is going to be equal to the integration of E, which is a vector, dot the area, ds or dA. This is the area. E dot dA. The area of the surface that you're calculating the flux on.
Surface area of the whole, the cube, the surface area of the whole cube.
Yes, whatever the shape is. Okay, if it's a plane surface like this, then this is the area. Okay. So when can we have, from that equation, look, just checking that equation. If you look at that equation, when can we have a zero flux?
When there is no electric field.
When there is no electric field, that's one. When there is no charge in the flux, that's one. And if that dot product give us zero, do you remember what is the dot product? So this is a good time to review vectors. If you have vector A dot vector B, A dot B, the resultant is A, B, cosine the angle between them. And this quantity is a scalar, or is it a vector quantity? A scalar quantity. Can you give us an example for something that we have studied before in Physics 111 that has a dot product? force dot displacement. The force dot the displacement, this is a scalar quantity. The dot product usually give us a scalar quantity. So now we know that the flux has to be a scalar quantity. And it's 0 when the cosine of that angle is 0. When that cosine is 0. Cosine is 0, 1. When theta equal to 90. That means that if the electric field perpendicular to the surface, phi is equal to 0. Good. Now, when the electric field is perpendicular to the surface, the electric flux is equal to 0. This is my surface. It's a plane surface. This is the surface. This is the electric field. Those are the electric field. The cover means the tip of the arrow. What is, do we have a flux?
No.
Do we have a flux? Who said yes? Who said no? Who's in? Amr saying, you're saying no, right? Yes. Who said no? Abdullah is saying no. He's a good student. He studies, so you should follow him. He's saying no, and Amr, this is the first time that he answered today. He's saying yes. Actually, I should follow Abdullah because he's a good student. But
That means I'm wrong.
am I right? Yeah. Oh, but Amr gave us the correct answer, but based on the wrong information, wrong assumption. Do not follow what I say. Perpendicular to the surface. What does perpendicular to the surface does? Look at this, at that point in here. There is an angle between the electric field and the area. Does the area have a direction? Thank you. Maureen is saying, right? Did I say your name right? Well, yes, an area has a direction and it's always out of the surface. So this is my surface. The direction of the area is this. This is the direction of the area. It's out of the surface, perpendicular to the surface. And if this is the electric field, what is the angle between them? 0. And if the angle between them is 0, the flux is maximum.
How does the area have a direction?
Area is a scalar quantity. Is it area a scalar quantity or is it a vector quantity? Is area a scalar? Okay. Is area a scalar quantity or is it a vector quantity? I claim, guys, that it is a vector quantity. Area is a vector quantity. And I think
It depends on the length and what they have scalars or vectors.
no. I think this is a good topic for research over the internet. So can you go and look at our internet? I want only 4 lines. 4 lines. Is area a scalar or a vector quantity? Only 4 lines. And please send them to me by email. Cut and paste from the internet is okay for this assignment if it's only 4 lines. So now, till we meet on Saturday and we'll discuss that again, the area. Trust me, for now, till Saturday. The area is a vector quantity and it has a direction. And the direction of the area, as Maureen said, it's always perpendicular to the surface, out of the surface, and out of the surface. So this is the direction of the area, and this is the direction of the electric field. The electric field, the flux now is a maximum value because the cosine angle theta is 1. Cosine 0 is 1. Now, if this is the area, and this is the electric field. This is the electric field, guys, going in that direction. What is the flux on that surface? It's 0. Because the area between the electric field and the surface is 90. The angle is 90, and
we can say here if the electric field is perpendicular to the direction of the surface, not the surface.
yeah, okay. Okay. Yes. Yes. Okay, guys. So now we know how to calculate the flux. It's that simple, integration. And if the electric field is constant, that's even better. If the electric field is constant, what happens to that integration? Then that integration will give us E dot dA, and the integration of dA is the area. Integration of the area, if the dA, small segment of the area, is the area, E dot A. So phi E, the electric flux will equal to E dot A only and only if the electric field is constant. But if it's not constant, then we have to do the integration.
So what's the meaning of an electric field is constant?
Do you remember that problem that I gave you of the simple pendulum that has electric field lines? This is a constant electric field. Constant electric field means the electric field, if we have electric field inside that room, and if I measure the electric field at that point, or I measure it in here, or in here, or at any point in the room, the electric field will be the same. But is the electric field from a point charge a constant electric field? Why not? Yes, because we know that the electric field from a point charge equal to K Q over R squared. You change R, the electric field change. So the electric field from a point charge is not a constant electric field, not a constant quantity. Later on, we'll find out that electric field from a plane, if you have a plane like this, and it has some charges on it, the electric field from that plane, infinite plane, is constant. We'll prove that. So now we know the flux. What is the definition of the flux? Number of field lines. We know how to calculate the electric flux. I'm going to skip that. And that as well. And let's solve those two problems together. We have a cube, has a side A, and we need to find, and that cube is inside a constant electric field. Sharif, again, when you see lines like that, equally spaced, and this means that this is a constant electric field. So that cube is inside a constant electric field. What is the flux?
0.
Why is it 0? Because the number of field lines n equal to the number of field lines out, so the total flux is equal to 0. How about number B? We have two spheres, two concentric spheres, and the center there is a charge Q. We need to compare the flux from on sphere 1 to that of sphere 2. And we have three answers. Phi on the smaller sphere, the flux on the smaller sphere is less than the flux on the larger sphere. The two fluxes are equal. The flux on the smaller sphere is more than the flux on the larger sphere. A, B, and C. Good. Good. This is good. Okay, Ala, another good student. He says that C, because the electric field will be much greater at here than there. Okay. So the electric field is going to be here. The electric field at the smaller sphere is stronger than the electric field at the larger sphere. Is this a correct statement?
It is.
Yes, it is. How did you know? Hey. We can listen to only one guy, so please. Abdullah, how did you know?
Because of the point charge formula.
Because from a point charge, the smaller the distance, the stronger the electric field. That's a good answer. Do you have another answer? Why the electric field here is stronger than the electric field at that sphere?
Because the more you're near to the positive charge, the more you're inside the global the charge.
The more you're closer to the charge, the more the stronger the electric field, which is the same as what Abdullah said. But if you remember, when we draw the field lines that's coming out from the charge or going into the charge, guys, back there, the closer the lines to each other, that means the stronger the field. The closer the lines to each other, the stronger the field. That's the second thing. So Ala said a statement that the electric field here is stronger than here. That's why this is the correct answer. That's Abdullah's explanation. Yes.
Why? The area will be bigger, and every electric field will be direct in the small one.
Who said that? Can you say that again out loud? He said, no, I'm not going to go do it. I will not do it mathematically. I forgot your name. Bishoy said, I will not calculate it. Look at it. It's the same number of field lines. It is the same number of field lines. And this is the definition of flux. It's the number of field lines. 1, 2, 3, 4, blah, blah, blah. Same numbers. Going through the two spheres. The flux are equal. That's one answer. That's a good answer. There is another way to solve that, which is go through this exercise. Which equation should I use? That or that?
The integration.
Look at the surface. Look at the surface. Along that surface, do we have a constant electric field? Yes. Same radius. Electric field is constant everywhere. Along that surface. Right? So from surface E1 is going to equal to K Q over R squared. Phi 1 equal to K Q over R squared times the area. Area. Sphere. Area of a sphere. 4 by R squared. That's the volume of a sphere. It's 4 over 3 by R cubed. Area of a sphere, not a circle. So if you look at this, the flux is equal to 4 pi K cubed. That's flux number 1. How about flux number 2?
KQ over 2R squared.
Phi 2 will equal to K Q divided by 2R all squared, right? Times 4 pi times 2R all squared. 4 pi K Q. So we got the same answer. Bishoy has told us a minute ago, but even without going into mathematics. Okay, good. This takes us to Gauss's law. Gauss's find by observation that the flux is not only equal to only equal to E dot dA but it's also equal to the charge inside any enclosed surface divided by a constant. By observation, Gauss found that the flux is not equal to what we just learned a minute ago, but also equal to the charge inside the surface divided by epsilon zero. The charge divided by epsilon zero. Let's go back to that example that we just looked at a minute ago. I'm going to leave that on the board. I'm going to go back on that example in here. I need to calculate the flux. I need to get a numerical value for the flux. Ala, I'm sorry. Can you move a little bit into the flux on the smaller sphere or on the larger one? Doesn't matter. I will choose the smaller one. Will equal to E, which is K Q over R squared times the area, which is 4 pi R squared. R will cancel out. You end up having 4 pi K. Can you remind me what is K? 1 over 4 pi epsilon 0 Q. Of course, do not memorize both up. It's going to be in the formula sheet. But trust me, even if you find it in the formula sheet, and if you don't really study, you're not going to be able to use it. The formula sheet is useless unless you study. Anyway, 4 pi will cancel out. You end up having Q over epsilon 0. So this is Gauss's law. Actually, Gauss's law, sometimes we write it in a different way. Sometimes we write it that way. Guys, we write it that way. Integration of E dot ds times epsilon 0 equal to the charge inside the surface. This is the primitivity of the medium. The electric field propagates inside materials in different ways. So this is characterized the material that the electric field propagates in. So epsilon 0, this is for vacuum or air. So now we're talking about vacuum or air. And if we have another material, then we'll change the value for epsilon 0. That's it. It's the primitivity of the medium. Okay, guys. Amir, ask. What integration? That one? What side? That? Oh, because I was here, I was calculating the flux on a sphere that has inside the charge Q. And I said that the electric field, so the flux, equal to the integration of E dot dA. The electric field along that surface is constant. It goes out of the integration. The integration over that area is the area of the sphere, which is 4 pi R squared. And this is so that is law. How useful is Gauss's law? Do you remember that problem that we took like 15 minutes to solve last time? A very long wire. and we needed to calculate the electric field at some distance from the wire. I'm going to start solving that problem again using Gauss's law. Closed surface. It has to be a closed surface. As I'll show you. It's the same thing. Sometimes this is an image, so I cut it and put it like this, so I was able to put the ring over the integration, but that needs closed surface. Sometimes when I write the equation, I'm not able to put that ring, so I put a square, which is the same thing, closed surface. Okay? Okay? What does that mean? I will explain it to you in a minute. Remember guys, last time we said that we need to calculate the electric field from a very long wire. And we spent like 15 minutes solving that problem. Let's try to solve that problem again using Gauss's law. We need to find the electric field. And if we know the flux and the area, we can find the electric field. So I'm going to assume that you have a very long wire, infinite wire, that has a charge Q on it. And we need to find the electric field from that wire. When we use Gauss's law, we have to have a symmetry. And if you look at any shapes, we're going to have either a spherical symmetry or cylindrical symmetry. That wire has a cylindrical symmetry. So if we draw a cylinder, imaginary virtual cylinder around that wire. And I'm going to call that cylinder Gauss's surface. This is Gauss's surface. Okay? Now, over that Gauss surface, we can calculate the flux. We should be able to find out the electric field. Gauss's law says that the integration over a closed surface for E dot the area of Gauss's surface equal to the charge inside, enclosed in Gauss surface divided by epsilon 0. This is Gauss's law. The flux, which is E dot the area of Gauss's surface equal to Q enclosed divided by epsilon 0. Before we go on, what is the direction of the electric field from that wire? We have agreed last time, if you remember, we have agreed that's always in that direction. It's always perpendicular to the wire. And if you don't remember, I can remind you again. Remember guys, we said this is the wire. This is the line of symmetry. If you choose a segment here, it will have an electric field in that direction. If you choose a similar segment here, it will have an electric field in that direction. Those two electric fields, the components along the x-axis will cancel out. The component along that axis will add up. So we'll have all the components along this. So from that wire, the electric field is always perpendicular in that direction. Now look at the cylinder. We need to calculate the flux on that cylinder, which is E dot dA. We have three surfaces. For that cylinder, we have three surfaces. Top, the bottom, and that round shape, the barrel. Right? We need to calculate the flux on each one of them and add them together. This is the total flux. This is what I mean by closed surface. The whole surface, top, bottom, and that round shape. This is that square or circle mean. So we need to calculate the flux on the top, on the bottom, and that shape. What is the flux on the top? Why is it 0? Because that's the area. And this is the electric field. So the electric field is perpendicular to the area, you get 0 flux on the top. Same on the top, on the bottom. How about this? First of all, the electric field is going to be constant because at that distance, the distance is the same all the time. So the electric field is constant. That means that the electric field goes out of the integration. That's one. This is the beauty of Gauss's law. If the electric field is constant, it's much more easier than using Coulomb's law. What is the area of that cylinder?
Pi r squared h.
No, that shape. 2 by r, 2 by r, which is that, times L, times H. Okay? That's the area of that round shape, not the cylinder, that shape, only that shape. It's 2 by r, which is the length of that, times H. Unless the electric field is actually, unless it's a sphere, it's going to be different. We'll see. Okay, guys? Now, this is the flux. This is the left-hand side. What is the right-hand side? What is the charge inside? Inside that cylinder. Wait. What is the charge inside that cylinder? How much charge is located, is enclosed inside that surface? It's your force uniform distribution.
Find the active field of each distance,
And
then add up the distance, H, the
okay. So I should add up all those dq's. KQ over r squared, this is for point charge. Yeah. I need to find how much charge. Again, guys, keep focused. I need to find how much charge inside that surface. The whole line has a charge Q.
Integration from the bottom to the top of the surface.
But, okay, that's a good way to do it. But if it's a uniform distribution, that means we have a charge density, which is the charge per unit length, equal to lambda. And if the length of the cylinder is h, then the total charge on the cylinder is the charge per unit length times the length of the cylinder. Correct? Divided by epsilon 0. Oh, which one of them? The epsilon 0 or the lambda h? Okay. Epsilon 0, that's it. Q include that lambda h. Now you have a wire, a whole wire, a wire that's 10 meter long. 10 meter, the wire that's 10 meter long. And has a charge of 10 coulombs. And that cylinder is only 3 meters. How much charge inside that cylinder? I'll say it again. We have a wire that's 10 meter long. And we have a charge that's 10 coulombs on that wire. Then you have that cylinder is only 3 meters. How much charge inside that cylinder? How did you get that? You calculate the charge density, which is the charge per unit length. How much charge is on 1 meter? This is the meaning of charge per unit length, which is 10 divided by 10, times the length of the cylinder. So the charge per unit length, which is lambda, charge density, times the length of the cylinder. This is Q. This is the charge inside the cylinder, divided by epsilon 0. So I'm just substituting by epsilon 0. Look at that equation. E will equal to H will cancel out, guys. It's lambda divided by 2 by epsilon r. This is exactly what we got last time. in only 1, 2, 3 steps without doing integration that we spent like 5 minutes doing it last time. So Gauss's law is a very useful tool only if we have symmetry. So I'm going to stop here. Do we have time? And I'll continue again on Saturday from 3 to 5, and I will post the room number on Blackboard.